Volatile tells the compiler that a variable may change by means it cannot see. Two situations produce that: a memory-mapped hardware register where the chip itself writes the value, and a variable modified by a signal handler, which can fire between any two instructions. Here is the hardware case. Status reg points at a fixed address on a microcontroller, and we spin until the bottom bit comes on. Now think about what an optimizer would do without the volatile. It reads the address once, sees that nothing in the loop body modifies it, keeps the value in a register, and turns your loop into either nothing at all or an infinite one. That is not a compiler bug by the rules of the language, it is a correct optimization, because as far as the compiler can prove, nothing changes. Volatile switches that off. It means reread the memory every single time, and do not reorder or remove my accesses. And now the warning, because this is one of the most widely believed pieces of wrong information in C. Volatile is not a threading primitive. It does not make anything atomic. A volatile count ++ is still a read, an add and a write, and two threads can still interleave those and lose an update. It provides no memory ordering, so the compiler and the processor are still free to move your other reads and writes around it. Two threads touching a volatile int is a data race, exactly as it would be without the keyword. All volatile promises is that each access really goes to memory, which is a much smaller guarantee than people assume. For shared state between threads, you want the atomic types in stdatomic.h or a mutex. Chapter 19 covers both. Volatile is for hardware registers and signal handlers, and outside those two cases you almost certainly do not want it. The third qualifier arrived in C99, and you will meet it far more often than you write it. Restrict is a promise to the optimizer for the lifetime of this pointer. The object it points at is accessed only through this pointer. Nothing else aliases it. That matters because without such a promise the compiler must assume any two pointers might point at the same memory. So after every write through one it has to reload through the other. Say so, and it can keep values in registers and vectorize the loop. The classic example is right there in memcopy's own signature. Both pointers are restrict, which is the standard's way of saying the source and destination must not overlap. That is why memcopy has undefined behavior on overlapping regions and why memmove exists for when they do. Powerful and easy to get wrong. Break the promise and the compiler will quietly generate wrong code with no warning. Use it when profiling tells you to, and not before.